Hello everyone, welcome to the lecture. In the last lecture, we started discussing about polyatomic molecules. We discussed about normal modes and looked into the spectrum of water and carbon dioxide. So, this is the spectrum or the IR spectrum of water and this is the IR spectrum of carbon dioxide. So, water has 3n minus 6, that is 3 times 3 minus 6, that is 3 vibrations, because water is nonlinear, and also 3 peaks are observed in the IR spectrum. For carbon dioxide, because carbon dioxide is linear, there are 3 n minus 5, that means 3 times 3 minus 5, that is 4 vibrations. However, only 2 peaks are observed in the IR spectrum. So, in this lecture, we will discuss the selection rules for vibrational spectroscopy and how these can be determined from the symmetries of the vibrational normal modes. The gross selection rule remains the same as that of the diatomic molecule. That is, the dipole moment must change as the vibration passes through the equilibrium position. Mathematically, this can be expressed as d mu dx at equilibrium position not equal to 0, where x is the displacement from the equilibrium position given by r minus r equilibrium. This selection rule is identical to that of a diatomic molecule, except that the displacement is now a combination of the atomic coordinates, that is the normal coordinate. So, the symmetric stretch of carbon dioxide. So, let us draw the symmetric stretch. So, here both the CO vibrations are in phase. So, this symmetric stretch of carbon dioxide is IR inactive, as it does not generate a dipole moment at any point during the vibration. This explains why there are only 2 vibrational bands in the infrared spectrum of carbon dioxide rather than 4. One is missing as the 2 bending modes are degenerate, and the second is missing as the symmetric stretch is IR inactive. So, now we will discuss the symmetries of vibrational wave functions. We want to look at the symmetries of the vibrational states in order to determine the selection rules for IR spectroscopy. We will be considering the vibrations of water. So, we see the water molecule in this figure and we will determine which water vibrations are IR active. Before we go into the details, we should understand that the application of symmetry arguments to molecules has the origin to something known as group theory. We would look into the basics of group theory from a more qualitative level. We will start with the elements of symmetry. So, let us look into the water molecule. In water, the rotation of the molecule by 2 pi by 2 radians. So, if we rotate this molecule along this axis by 2 pi by 2 radians, it produces an identical configuration to the observer. So, if I write this as H 1 and H 2, and if I do a 2 pi by 2 rotation around the axis, what I get is H 1 on the right side and H 2 on the left side. But because these hydrogen atoms are indistinguishable, we cannot distinguish between the conformer before the rotation and the conformer after the rotation. In other words, rotation of any molecule by 2 pi by n radians, where n can be 1, 2 dot 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 up to infinity about an axis, if produces an equivalent configuration which to a stationary observer is indistinguishable from the initial one, the molecule has an n-fold axis of symmetry, and the symbol for such a symmetry is given by C n. So, like C n, there are other elements of symmetry. If a molecule has a plane of symmetry such that reflection of all the nuclei through the plane to an equal distance on the opposite side produces a configuration indistinguishable from the initial one, it is known as the plane of symmetry, and the symbol for such symmetry is given by sigma. So, let us look again into water. So, in this figure the axes are labeled. So, we have this as the z axis and this as the y axis. So, the water, which is a planar molecule, the vertical axis in this plane is the z axis and the horizontal axis is the y axis, and the axis that is going below and up the plane of the water molecule is the x axis. The subscript v in this sigmas stand for vertical, which implies that the plane is vertical with respect with the highest fold axis, that is the C2 axis or the z axis in this case, and this defines the vertical direction. Moreover, all the molecules possess the identity element of symmetry. So, this identity element is given by I. So, there are several other symmetry elements for more complex molecules, more complex than water. However, as we limit our discussion to water, the elements of symmetry that water has are C2, sigma v along the x z plane, sigma v along the y z plane, and I. The symmetry elements of a molecule constitute something known as the point group. The point groups are so called because when all the operations of the group are carried out, at least one point is unaffected. In this particular case of water, any point on the C2 axis is unaffected. So, as water contains one C2 axis, so water contains one C2 axis and two sigma planes of symmetry, all of which contain the C2 axis, water belongs to the C2V point group. if the element of symmetry of the wave function is preserved during a symmetry operation, the symmetry operation has no effect on the wave function. And because the symmetry operation has no effect on the wave function, we can write psi v, which is the wave function, after the symmetry operation remains the same, that is plus 1 times psi v. Thus, we can say that psi v is symmetric to the symmetry operation. On the other hand, if the wave function changes sign by carrying out the operation, so psi v changes sign during the operation, so it becomes minus 1 times psi v, we can say that psi v is anti-symmetric to the symmetry operation. So, for the water molecule, the C2 and the sigma v x z operations have no effect on the wave function. So, we can create something known as the character table, where the elements, that is this plus 1 or minus 1 of this character table are known as the characters of symmetry operation with respect to the symmetry operation. So, here we show the character table of water or the C2V point group. The character with respect to I must always be plus 1, because this is an identity operation. We can see that sigma v y z is generated from C2 and sigma v x z. That means, if we have the water molecule and we perform the C2 operation and also perform the sigma v x z operation, then what we end up with is sigma v y z operation. So, thus the characters with respect to sigma v y z is the product of characters with respect to C2 and sigma v x z. So, we can see here that when C2 and sigma v x z both are plus 1, the sigma v y z is plus 1. When they are both minus 1, the product again is plus 1. However, when this C2 is plus 1 and sigma v is minus 1, the product is minus 1, and here also when C2 is minus 1 and sigma v is plus 1, then sigma v y z, here the product is minus 1. So, each of these 4 rows of characters is called the irreducible representation. This is the irreducible representation of the group, and for convenience each is represented by a symmetry species, that is A1, A2, B1 and B2. The A1 species is said to be totally symmetric, since all the characters are plus 1. The other 3 species are not totally symmetric. The symmetry species labels are conventional. A or B indicates symmetry or anti-symmetry respectively to C2. So, we can see whenever C2 is plus 1, we have A, and whenever C2 is minus 1, we have B. Similarly, the subscripts 1 and 2 indicate symmetry or antisymmetry with respect to the sigma v x z plane. So, we can see whenever the sigma v x z is plus 1, we have 1, and when it is minus 1, we have 2. The water molecule has 3 normal modes of vibration as shown in this figure. So, we can label these modes. So, the first one is the symmetric stretch, the second one is the asymmetric stretch, and the third one is the bending mode. So, using the C2V character table, the wave functions psi v for each can be easily assigned to symmetry species. The symmetric stretch can be identified as the displacement in both these OH bonds, where both these OH bonds are in phase, the displacements are in phase with each other. The normal mode has A1 symmetry, because now if we plot the C2 axis as well as if we plot the sigma v x z plane, it produces, or the symmetry operations produce identical configurations. So, this has A1 symmetry. So, we can see this is because the mode is symmetric to both C2 and sigma v x z symmetry operations. The asymmetric stretch shown here can be identified as the vibration in which the displacements of the OH bonds are out of phase with each other. The normal mode is antisymmetric with respect to C2 or the sigma v x z plane, and because it is antisymmetric to both C2 and sigma v x z. So, because of the antisymmetry to C2, we have B, and antisymmetry to sigma v, we have B2. So, it has the B2 symmetry. The bending vibration is the vibration in which the HOH angle is increasing and decreasing. As we can see, this normal mode is also symmetric with respect to C2 and the sigma v x z plane, and because it is symmetric to all these symmetry operations, it has A1 symmetry. So, now let us look at the ground vibrational state, that means at v equals 0, and the wave function of this v equals 0 can be represented by psi 0, which is proportional to exponential of minus q squared by 2. So, here q is the mass weighted coordinate. If we apply any symmetry operator to this function, then q may change sign. For example, the antisymmetric stretch with B2 symmetry is antisymmetric with respect to the C2 operation. However, the q squared is always symmetric, and thus this psi 0 is totally symmetric or we can say psi 0 is A 1 for water. Now, let us look into the excited vibrational states. So, the first two vibrational excited states can be represented by psi 1 and psi 2. So, psi 1 can be represented as proportional to q times exponential minus q squared by 2, and psi 2 is proportional to q squared minus 1 times exponential minus q squared by 2. Thus, psi 1 is the product of q which has B2 symmetry, and this part is psi 0 and psi 0 has A1 symmetry. Thus, psi 1 for the asymmetric stretch has B2 times A1, that is B2 symmetry overall. The V equals 2 state has the A1 symmetry like the ground state, because here we are dealing with only q squared. So, it can be seen that in fact, psi V has B2 symmetry when V is odd and A1 symmetry when V is even. The bent and the symmetric stretch both has A1 symmetry, and since A1 times A1 is also equal to A1, all their states have A1 symmetry. So, how does identifying the symmetry of the vibrational states help us identify the selection rules? We know that the intensity of a transition is proportional to the square of the transition dipole moment, and this transition moment is given by integration of the final state, that is psi star final, the dipole moment operator, the initial state, that is psi I d tau. By definition, an integral is just a number. Just symmetry operations have no effect on it, but the integrand may be operated by the symmetry operators, and if there is any symmetry operator that changes the sign, it will change the sign of the whole integral. So, there is a contradiction unless the integral is 0. So, the integrand must have an overall A1 symmetry. In other words, it must be totally symmetric if it has to be non-zero. The dipole moment mu, because we have this dipole moment operator. So, this mu can be broken down to mu x, mu y and mu z. So, this mu x can be written as the sum of the charges times the x coordinate of the charges. So, based on the choice of our axis, so this x, y and z coordinates of the C2V has B1, B2 and A1 symmetry. So, the mu x, mu y, mu z, they also have B1, B2 and A1 symmetries. As we have already discussed, the vibrational states of water has either A1, that is when V equals even, or B2, that is when V equals odd symmetries. So, we can construct the possible symmetries of the integrand of the transition dipole moment. So, here we are constructing the possible integrand. So, here we have the components of the dipole moment, and in the second column we are having the symmetries of vibrational transitions, and in the third column we are constructing the entire symmetry of the integrand. So, we can see that mu x is B1. So, if we have a transition from A1 to A1, then our triple product becomes A1 times B1 times A1, and this is B1. And as we know, the total integrand has to be A1, that means this case is forbidden. So, we have to find out where this integrand is totally symmetric. So, we can see that there are only 3 cases where the transitions are allowed. As the number of vibrations in water is equal to the number of allowed transitions, all the vibrations in water are IR active. Thus, in today's lecture, we have used the symmetries of the vibrational states to gain insight about the selection rules.